Hello. Now we are starting a new chapter, chapter 3, entitled as Measures of Location. So title is sounds more difficult, but it's about average. So it'll be maybe still easy enough to most of you guys. So let's sum up what we have done in the previous chapters, and let's preview what we are going to do in this chapter. In the previous chapters, 1 and 2, we learned probabilities. Probabilities, conditional probabilities, and there are some rules about them, how to calculate them, and some how to convert between them. And in this chapter, we are going to learn averages and its alternatives or variations. The probabilities and averages are both have the same. They have the same purpose. Mainly, they are to summarize the data. They usually serve as a summary of data. So you can think like roughly speaking, any kind of analyst, to the best of my knowledge, in statistics, everything is some kind of average or some kind of probability. So that's pretty much everything in statistics. And average is also very useful. In some cases, it's much more useful than probabilities. So we are going to think about the underlying structures for average and how to define that, and what we have to be careful when we use averages. The relevant chapters from the textbooks are these, and usually in the textbooks, the averages come earlier than probabilities, but I don't like that idea, because if you study mathematical fundamentals of statistics, probability should come first. The randomness is defined based on probabilities, the experiment, event, outcome, sample space. These are the very basic fundamentals, and then the averages are defined upon the probabilities. So what I'm doing is more theoretically consistent with higher level statistics. Anyhow, if you are interested, refer to these chapters. Let me start with a brain teaser. Consider some data on used cars which are listed for sale, and we have information on these variables. First, the listed price and their make and models, and the model year, and the mileage, and the number of major repairs done on the used car. And a simple question. One variable among these 5, there is one variable that does not have the average. What is that? The other 4 have their averages, but one variable does not have its average. Find it. That's just a brain warmer, so there is no serious theory behind it. The answer is B, make and model. So make and model means like Honda, Toyota, Ford, GM, these brands like Camry, Tesla, Model 3, something like that. So these kind of variables cannot be calculated for the average, because there is no average between, for example, Ford and GM. What is the average between them? There is no average. To calculate the average, they must be numbers. Like the average between 1 and 3 is 2. Because they are numbers, we can compare them, we can add them, we can find there in the middle of them. Where is the middle of them? So uh, so we classify the variables into two categories. First, the first type of variables is categorical or qualitative variables. That's make and model, like Camry Model 3 or like Accord, like Rev4. These are models. They are variables. When I ask you, when I ask when I randomly choose a car, you can record the model. So it is a variable with like having no problem. There is no problem in making the data, but you cannot calculate the average. And on the other hand, the other type of data, the other type of variables is numerical variables or quantitative variables. Literally, they are numbers. Like mileages, let's go back here. Price, it's a number. Model year is a number. Mileage is a number. Number of major repairs is a number. So when you have numbers, you can add them, you can compare them, you can measure the distance between them, and there are many things you can do. You can manipulate them because they are numbers. So having numbers is important when you analyze the data. So many methods are based on the assumption that the variable is numerical. For example, averages, maximum or minimum, variance and standard deviation, median, and percentiles. It doesn't matter if you don't know what they are. Just put some of them are popular, and you know many of them. So like maximum and minimum. To calculate maximum and minimum, you should be able to compare different values, and you cannot compare what if so which is greater between Ford and Tesla. We cannot say anything. We need numbers. We need numbers to calculate the maximum. And similarly, variance, standard deviation, median, percentiles, those are the main topics in chapter 3 and 4. So we are going to study these guys under the assumption that the variables are numerical. So from now on, in this chapter and in the next chapter, and also maybe from now on through the end till the end of this semester, maybe all the examples will consider numerical variables. Even if it's not numerical, still you have to quantify the outcomes. So we are going to assume numbers. And so here comes a new term, random variable. Random variable is a variable which is a number. So it is a description of the outcome, but from an experiment, but it should be a number. So that's what we call a random variable. For example, there is nothing special. If you toss a coin, then in the previous chapter when you define probability, it does not matter whether how you call this. You may call the outcome as head and tail. Not a problem. The outcomes are head and tail, but they are not numbers. Now, from now on, we have to call them 0 and 1. Head may be 0 or tail may be 0. It does not matter. You have to define as you want. Like you may define head as 1 or tail as 1. Does not matter, but you have to define in one of the two ways. And dice, if you roll a dice, it's kind of natural. The outcomes are automatically numbers. And YouTube video counts, view counts, if you choose a random video, YouTube video, and see its view counts, and its outcome can be any integers, non-negative integers. The view can be 0 or 1, 2, 3, it could be any number, any positive integers. So also it has a natural numerical description of the outcome. And if you think about stock return, Also, stop return is represented by a percentage in the unit of percentage, but still it is a number. So the sample space is usually a rational number. It could be minus, could be negative, could be positive. So in many examples, the random variables are very naturally defined. So you don't need to worry about how to define random variable. It's pretty much given. Just it's a kind of scientific term, academic term to make things more difficult. And usually random variables are denoted as x or y or z. Typically, these numbers are reserved for random variables in statistics. And probability, it's also easy to define probability once you have numbers. You may define probability as probability the random variable equals to something, or smaller than something, greater than something, greater than or equal to, smaller than or equal to, or in between two numbers. So now the probability, so the event is defined by inequalities or equality. And a minor notation rule in policies that I'm going to use. So when you think about this, it is the probability that a random variable x equals to a value small x. So in this case, I used uppercase letters here and here. So when you read it, when you read this probability, the random variable x is undetermined, unrealized object. Or if you think about the probability that the number on the dice equals 6. When you say this sentence, the number on the dice is random variable. It's undetermined. Can be any number between 1 and 6. So that is the random object. The randomness lies in these guys, and that is denoted by an uppercase letter. But I use lowercase letters when I need to specify a certain number, non-random number. For example, when you define a probability for a dice, you have to define the outcome. Like here, probability from a dice equals what is the probability that the outcome equals 6. Then you have to specify one number to calculate the probability. And in this case, 6 is not a random object. It is just a value that you are interested in. So we are going to use lowercase letters for these kind of specific values. It's not a problem, not a big problem at all, but I will try to be consistent throughout the semester and in slides so that you understand the basic structure of the notation and the mathematical logic. And in many cases, it's obvious what random variable I'm referring to. So probability that random variable x equals to a value x will be abbreviated to probability of lowercase x. So it does not matter. I'm going to drop this part. Not a big problem in many contexts. And a data set usually has multiple observations, and they are denoted by x subscript indexes. So x1, x2, x3 up to xn. So you can imagine this way. When you throw a dice 100 times, then you will have 100 observations at the end. But before doing that experiment, you still would like to think about their probability and their expectations, averages. Then mathematically, we are going to denote them as x1, x2, x3, x100. So this is our notation, and we are going to study more about averages. We have not discussed anything on averages in this video, and we will start with an example from the next video. So Thank you for watching and see you in the next video.